My name is Steve Bromley. I'm a postdoc working with Mike Fogel and Dennis Bodowitz at Auburn University. And this project, COLTRIMS measurements of charge exchange with highly charged ions, was something that was presented at a previous AtomDB several years ago by Mike Fogel, back when this was in the planning stage. I am now happy to report that we are well underway in bringing this project together. We are trying to do velocity resolved measurements of charge exchange. As some people have pointed out earlier, the solar wind contains highly charged ions of things like carbon, nitrogen, and oxygen, as well as trace heavy metals, things like iron or magnesium. They ultimately, whenever you have these hot gases interacting with a cold gas, you are going to have charge exchange. And those neutrals can be anything from atomic hydrogen up to something very complex, like, say, CO2. And there are a number of theoretical treatments available for calculating what these cross-sections should be and producing the resulting X-ray cascade spectra. But these are only approximations, and they ultimately need to be benchmarked against some experimental measurements. In particular, for bare ions interacting with neutrals, following the electron capture, the L states are degenerate. And so while they won't have an effect on the exact positions of emission lines, they will affect intensities, and this line ratio is used for diagnostic purposes. And so we would like to do these, what is called a COLTRIMS, or cold target recoil ion momentum spectroscopy measurement, where we cross a highly charged ion beam with a cold neutral gas jet. Downstream from this interaction region, we will separate out the charge exchange ions from the highly charged ion beam. So not only will we separate out the primary beam, but also, say, the Q-1 and Q-2 charge states that are produced by electron capture. At the same time, we will do time of flight spectroscopy on the recoil ions, and from the momentum changes of both the primary beam and the slow ions, we can calculate what the N distribution of the capture states is. At the same time, an X-ray spectrometer will capture the spectra, and from that we can uncover the L distribution, which we can then use to directly benchmark the theoretical work. And I had mentioned this before. This collaboration is from a number of universities. We have Clemson University is providing their qubit beamline, their EBIT plus their beamline. Auburn University is providing the COLTRIMS apparatus, so all of the microchannel plates for detecting the particles and all of the deflection schemes. NASA Goddard and Livermore is providing a microcalorimeter for the X-ray spectra. And the University of Georgia is handling all of the theoretical calculations of the cross-sections and the X-ray spectra. And so this summer and this fall, we are finishing putting together some of the deflection apparatuses. At the moment, some of those parts are at our machine shop waiting to get made. This coming fall, we'll be testing all the electronics as well as all the detectors here. In the spring, we will be transferring everything to Clemson and preparing that for the summer campaign, which we expect we'll first be doing measurements with neon, and time permitting, we'll explore other neutrals. And so on the right, in my last minute or so remaining, I have a quick schematic of how this whole experiment is laid out. For something like neon, those experiments should be fairly simple to do. We can just inject gaseous neon into the system. But for metals like iron or magnesium, those can be a bit trickier to get into an EBIT. And so our collaborators at Clemson are exploring a couple different methods: thermal evaporation, laser ablation, and also volatile organic compounds. And so if there are any questions, I will be more than happy to answer them in the Slack. Or my email is also listed at the top of the poster, right under the Alder list. And thank you for your time.